Hello everyone, welcome to SJC content. This is Dr. Jethruth Emelda Mary, Assistant Professor in Mathematics, St.Joseph College of Arts and Science, Autonomous Cuddalore. In this video lecture, we are going to discuss about a dynamic programming problem, Model 3 in mathematical programming for first MSc Mathematics. In the previous video lecture, we have seen what is dynamic programming problem and what are the terms involved in the dynamic programming and concept of the dynamic programming, some examples. There are several methods available in this dynamic programming technique, in which I have taken the model 3, namely we call it as additive separable return function and single additive constraints. The general form of the separable return function is given as defined as minima z equal to f1 of d1 plus f2 of d2 plus etc. fn of dn subject to the constraints a1 d1 plus a2 d2 plus etc. an dn, which is greater than b, where f1 of d1 comma f2 of d2 etc. fn of dn are separable return functions and a1 a2 etc. an are constants, d1 d2 etc. dn are decision variables. So to solve the problem using dynamic programming technique, we need to define state variables. As there are n decision variables or separable return functions, we need to define n state variables s1, s2 etc. xn such a way that sn equal to a1 d1 plus a2 d2 etc. an dn. Sn minus 1 is sn minus an dn, and therefore sj is equal to sj minus 1 minus aj dj. Here we have to define a recursive equation. So for stage 1, the recursive equation is denoted by f1 of 1 and is defined as minimum of f1 of d1. For stage 2, f2 of s2 is equal to minimum of f1 of d1 plus f2 of d2. Or we shall write f1 of d1 plus f1 star of d1 or s1. In nth stage, we shall define the recursive equation as fn star of or fn of sn is equal to fn of sn equal to minimum of fn of sn plus fn minus 1 star of sn minus 1. Here, using the previous concept, we are going to solve the following problem. Use dynamic programming to show that p1 log p1 plus p2 log p2 plus extra pn log pn is minimum with respect to the constraints p1 plus p2 plus extra pn equal to 1 by n. We shall solve this problem using dynamic programming technique, namely this is the given problem is of type model 3, additive separable return function and single additive constraints. Since there are n decision variables, so we need to introduce n state variables, and we shall solve this problem using n stage problem. For each stage we have to form a recursive equation. After forming a recursive equation, we have to find the solution for each recursive equation. Finally we get the optimal solution for the recursive equation. For that, let us define the recursive equation for stage n equal to 1, f1 of 1 equal to 1 log 1. Similarly, for stage 2, we define f2 of 1 is equal to p1 log p1 plus p2 log p2, or we shall write this as z log z plus 1 minus z log 1 minus z, such that p1 plus p2 equal to 1, where p1 equal to z and p2 equals 1 minus z. Proceeding in the same way, we shall define the nth recursive equation, the general recursive equation for nth stage. Fn of 1 equal to minimum of fn of pn log pn plus fn minus 1 of 1 minus z. Now we find the solution to the recursive equation. Let us consider the second stage problem. f2 of 1 is equal to p1 log p1 plus p2 log p2, or otherwise we write z log z plus 1 minus z log 1 minus z. Let us take y is equal to z log z plus 1 minus z log 1 minus z and find the minimum value for y. For that, let us differentiate y with respect to z, namely we get a first order derivative and equate them to 0, find the value of z. Then you find the second order derivative, d squared y by dz squared. Just find the values of d squared y by dx z squared. If it is greater than 0, we conclude the function attains minimum. So here the function attains minimum for which z equal to 1 by n. Similarly, proceeding with the same way, we shall find the recursive solution to the nth stage. We found that the minimum value of the function p1 log p1 plus p2 log p2 plus extra pn log pn is fn of 1 is equal to n into 1 by n log 1 by n, for which p1 equal to p2 equal to etc. pn equal to 1 by n. So the above result can be proved for any value of n by using mathematical inductions. So let us take n equal to m plus 1. So f1 of m plus 1 or fm plus 1 of 1 equal to minimum of z log z plus fm of 1 minus z. We know that is minimum of namely fn of 1 minus z is m times of 1 minus z by m log 1 minus z by m. That is f of z equal to log z plus 1 minus z by m log 1 minus z by m, or we shall write fm plus 1 equal to 1 by m plus 1 log 1 plus 1 by m plus 1 plus m times of 1 by m plus 1 log 1 by m plus 1. Combining these two, we hit m plus 1 times of 1 by m plus 1 log 1 by m plus 1. So this is the result when n equal to m plus 1. We'll move to the next problem. Use dynamic programming to solve the following problem. Minimize z equal to y1 square plus y2 square plus y3 square. Subject to the constraints y1 plus y2 plus y3 is equal to 10 and y1, y2, y3 greater than or equal to 0. Let us solve this problem using 3 stage. For that, we introduce 3 state variable s1, s2, s3 and define the state variable s3 as y1 plus y2 plus y3 equal to 15 and s2 is equal to y1 plus y2. We shall write this is s3 minus y3 and s1 is equal to y1. Again, we will write s1 as s2 minus y2. Now, if we define the recursive equation, that can be written as f2 of s2 is equal to minimum of y1 squared plus y2 squared, or we will write y1 squared plus f1 of s1, where f1 of s1 is minimum of y1 squared, where y1 squared can be replaced by s2 minus y2 the whole square. Therefore, the recursive equation of second stage problem, now we consider the second stage problem to find the optimal solution. So f2 of s2 is minimum of y2 square plus s2 minus y2 the whole square. Using differential calculus, we just find the minimum value as follows. f2 of s2 is equal to s2 by 2 the whole square plus s2 minus s2 by 2 the whole square. Simplifying, we get this is y2 squared plus s2 minus or y3 squared plus s1 squared by y2 for third stage problem. The recursive equation or the optimal solution for third stage is obtained as follows. Finally, we got minimum of y3 square plus s2 minus y2 by 2. Again, differentiating, we found that the optimal value or the minimum value of third stage or third recursive equation is s3 squared by 3. But for minimum value of f3 of s3, we must have y1 plus y2 plus y3 equal to 10. Hence, f3 of s3 is 10 squared by 3 or 100 by 3, where y3 equal to s3 by 3, that is 10 by 3. And already you know y2 equal to s2 by 2, that is s3 minus y3 by 2. Simplifying, we get this is 10 by 3. Similarly, we found y1 is equal to 10 by 3. Hence, we conclude that the minimum value of y1 square plus y2 square plus y3 square is 100 by 3 for y1 equal to y2 equal to y3 equal to 10 by 3. Next is another problem. Use dynamic programming problem to solve the following. Minimize z equal to y1 square plus y2 square plus y3 square. Subject to the constraints y1 plus y2 plus y3 greater than or equal to 15. Solve the problem using the previous concept. Thank you for watching this video.